Welcome, I will talk about the multi-node workloads within EVEREST project. So our task is quite simple. We will just want to take a program and run it on some computational resources, on some node. And in this visual notion, I will draw a program as a rectangle and the node as a hexagonal shape. And so what is the problem? We actually have more nodes. Maybe they are part of the cluster, maybe they are some independent machines, it doesn't matter. We have more independent computers and we want to still utilize them and run our program there. So this is our main motivation, and the complications are the right side of the picture. But there are also some complications in the left part, which is that we maybe have some more complex pipeline, like first I have to run something, then I have to run something else, maybe something can run in parallel and so on. I have some dependencies between the programs, and still I want to be able to somehow schedule this program on the nodes in a way that's efficient and so on. What makes the whole task even more complex is that heterogeneity. So basically, some nodes may have some capabilities or resources that other nodes does not have, or basically they have less memory than others and so on. So we have some heterogeneous nodes, but also there is heterogeneity on the program side. So some programs may be long running, some programs are short running, some programs may have some specific resource requirements, so they have to run on the machine that has some kind of special hardware, let's say. And still, I want to be able to efficiently schedule it on the hardware, on the nodes that I have available. So this is our problem statement. What are the challenges? Yeah, we have the complex irregular tasks, we have a complex resources, and we have to be able to match with resource requests on the resources and the tasks. But we also want to support the many tasks. Like, we don't want to limit it too much the user of in the number of tasks, because if the system supports only like few tasks, the problem is that then the user has to manually aggregate tasks together, and it can be quite error prone, and you are also preventing some dynamicity and load balancing, and if the user somehow divide the resources in the wrong way, also you can have a lot of performance loss. So we want to support basically to be able to do as many tasks as possible, and user does not have to care too much about how many tasks they are producing. So this is one thing. Another thing is this dynamic load balancing. So we want to react on what the situation on the cluster or on the nodes is actually happening. So if something terminates earlier, we want to be able to utilize these resources for other computations and do some work stealing from other ones. So we don't want to be fixed on some static decision at the beginning. We want to react dynamically on what is actually going on and utilize the resources as much as possible. So this is challenging. So how to look from the architecture point of view? At the top, there is an EVEREST user code, which is basically your application that are using our tools. And for the multi-node, there is the FKit. FKit is just the Python library that provides some simple API. There are basically two APIs. One is mimicking Dask back API. Dask is quite popular library in data processing in Python. So we are providing some drop-in replacement for the API of the subset of the API, and also we are providing some simple API that we call distribute, which is for some simple distribution of the tasks, and I will show it to you later. What FKit basically does, it one thing is that it provides the API, and once you call this API, it will compose in background the task graph. The task graph is like a graph that captures the dependencies, but it does not capture actual on which machine we want to run. It's independent on the computational cluster. It just says, we are just saying like, oh, first I need to compute A, then I want to compute B, and you can also specify some resources. And the A needs 5 CPUs and B needs some FPGA or something like this. This graph is input to the Hyperq server. Hyperq is the component which do all the heavy lifting there, and we will see how it works. So once again, we will put the task into Hyperq server, which is running somewhere in the cluster. There's the scheduler. There is a component that we call taco. In the taco, there is a scheduler that distributes, that computes where we want to run what. Hyperq server realizes this decision, and it will connect. It will on the machines where the computation should actually run. We have to start the Hyperq worker. I will show you later how to do it. And once the worker is connected to the server, if there is some work, gives the work to the Hyperq worker. Inside the Hyperq worker is another part of the fkit which will create some environment where the task can be started and start the actual task. And in this picture, we also have this data transfer that for the actual data exchange, the workers communicate directly. It does not go through the Hyperq server. Hyperq server is basically the coordination thing, but not for the data itself. So just to recap, we have two components: fkit, which is some kind of gateway for the whole thing, and submits things to the Hyperq. So first I will start how to use and deploy Hyperq. Now we will talk about Hyperq and how to deploy it and start simple tasking. First we will start on deploying on the desktop machine, but then I will show you how to deploy it on the cluster. So Hyperq is available on this location, and what you need to do is just to download from the releases, like latest version, choose your platform, and actually it's just simple binary, no dependencies are required. You just need to decompress the archive and start the binary. On the EVEREST clusters, Hyperq is already pre-installed, but it's not a problem to just download your own version and just to start it. So everything is actually operated through the binary named Hyperq, and I will show you right now. So once we have downloaded the Hyperq, first thing we need to start the server, which is the central element of whole computation. And in the case of the clusters, we will start it on the login node, but you can run it anywhere else. Now on this local installation, I will just start it on my local machine. So as I said, everything is operated through the HQ command, HQ binary, and the command for the starting server is the HQ server start. So what happens now? The server is running and it creates some access file. This access file actually contains some information where the server is running, how to connect workers there, and so on. But the important thing is the secrets. So it allows to authentication of the connection. So because of the secret, you can submit jobs or connect workers, and without this information, you cannot do it. So if you want to share the server with someone else, you just need to send this file to other users, but you have also trust them, because then they can start their own jobs, and jobs can actually do anything. You just start the jobs which can run some binary or Python script or whatever, so we have to trust them. This secret basically allows us that thing. If you do not have an access, you cannot do anything. You will just see that the service is running. This is the access file, and you can start multiple instances of the server, and each of them will have own access files, and you can specify which access file you want, but by default, because I haven't specified any path, it will create the access file in my home directory, and so I will not specify any access file in the following commands, because by default it will search for the access file in the default path. So now the next thing what we have to do is to submit jobs or connect workers. So first I will show you how to connect workers, but you can do it vice versa. First you may submit the task and then connect workers. It doesn't matter. So we have the worker is running, and the server is running, and now we will need to connect the first worker, which can be done if you want just the default worker, HQ, worker start. I will do it in the background. So it searches for the access file in the different location, reads it reads from the file where the server is running, it connects to the server and registers the server. It also detects some resources, and this particular machine it has 4 CPUs, single GPU, and some memory, and it's also propagated to the system. Now I can connect to some another machine, and if the machine also has access to the file with the keys, I can start another worker. I will not do it for the demonstration purpose on the same machine, but it doesn't make much sense for the practical computation. But this is just for the demonstration that I can start multiple workers. So now I can see that I can list all workers by HQ worker list, which tells me, okay, there are 2 running workers. They are actually on the same machine for this demonstration purpose. They have, each of them has 4 CPUs, GPUs, memory, and so on. Yeah, there is also manager section. It will be more important on the cluster. It's basically the outer manager like EVEREST or Slurm. But as I manually started the workers, there are no manager. I can also see some details about each individual worker. So like info, and now the ID is 1 or 2. So let's look on the 1. So, yeah, we see more detailed information. So we have workers. So now we need to submit some tasks, and the most simple way is to do it through the command line and just submit sleep 1. I will just submit this is the part of the HQ submit. This is the fixed part of the Hypercube, and the sleep 1 is name. And this is the name of the binary, and there are some means. So it will just basically run on some node. Yeah, this simple program. So HQ made 1, and job was successfully submitted. It will be very fast. So now if I will just list of all jobs, and there is, by default it will show you only running or waiting jobs, but it's already finished, so I will list all. So I have one finished job, and I can also look on more details about the job and info and the ID of the job. It's finished. By default, it asks for one CPU. I will show you later how to ask for more. Yeah, there was some working directories and so on, and 0 priority. I can also submit more tasks in one job at once. It's basically array job, like this. Submit array, and I will let's do it like this. So HQ submit. Now I want to task from 1 to 20, and each of them will sleep for 2 seconds. Submit it. See how the jobs are progressing, and now I catch it in the moment for running, and 61 is already finished. Now probably all of them is finished. So this is how the job can be submitted. Whole thing is dynamic. If I will start more workers or kill some of the workers, like here I just started 2 workers, so it was automatically spread on both of the workers. But if one of them is killed, then of course I will lose the actual computation, but all tasks that were assigned to this worker is dynamically rescheduled to the remaining worker. If I add some additional workers, again there will be some work stealing, and the work from one worker will be distributed to the new ones if there is enough work. So this is how it looks like from the basic perspective. What we can do next is we can specify more resources. Right now, this task run 20. This job has 20 tasks, and each of them needs 1 CPU. But I can specify some more details constraints, like okay, I need 4 CPUs and 1, and now it allocates the 4 CPUs for the job. Of course, I can ask even for some large number of the CPUs, but then in this case, as long as this cannot be fulfilled, because if we look again on my workers, I will just see that each of them has 4 CPUs, and we have node 128. We cannot run the task that demands 128 cores. So if I will run it, if I will show you a list of the tasks, this job is waiting and it cannot be run because there is no worker at all that can run the job with so many CPUs. But if I will connect the worker with sufficiently many CPUs, it will be immediately started. So let's look more about the configuration of the worker. Here I started the worker in the most simple way. I just use worker start, but I can specify some more details. One important thing is time limit. Idle timeout. And let's say set it to the 10 minutes. sorry, timeout. Idle timeout. And right now, I started the ordinary worker, but this worker will be automatically switched off if there will be window of the 10 minutes that no task is submitted to this worker. So it can be useful that you just ask for some resources, submit some jobs, some tasks, and yeah, if you have it will be automatically switched off after some time limit, and you don't have to care about the switching of the workers. So this is one option, and the second option is that it automatically detects some resources. It detects, in my case here, one GPU, some memory, and CPUs, but you can also specify your own resources that can be purely virtual or something that you can that cannot be detected automatically. And it is done in the following ways. So I will just specify resources and the name of the resource, let's say FPGA, and now there are two types of kind of resources. One is that I just want to provide some limited resources like a memory. So I just have to care about the sum. That is not that some of the tasks will not use more than the specified that what the worker is actually providing, but the other type is indices. This is basically named resources. So if I have more FPGAs or GPUs, so I want to distinguish all of them, right? And pin the tasks for each individual resource. So what I want to say is that if I start the task and I want to with this particular resource, I want to say this task, oh, please use this FPGA or use this GPU or use this particular resource. And we call it indices. So it's basically indexed by some numbers. And let's say now I will declare that I have resource name FPGAs, and the indices are 0, 1, and 2. Sorry, not resources, but resource. So I declare this new FPGA resource, and when I want to submit, if I want some of this resource or that I have just defined, I can just HQ submit, and previously we asked for some CPUs. We still can do it, but I can ask for FPGA, and I want one FPGA. Now let's again use our dummy tasks with one. And it's finished because it has a worker where we can run it, which was the worker that was executed last. Okay, so this is the way how we can define resources. So this was how you can simply start Hyperq, start the workers, and submit the jobs, and this is it. Now I will show you how to use Hyperq on HPC infrastructure. Actually, the supercomputer is usually just composed from many nodes, and I will demonstrate it to you on our Carolina supercomputer. Here you can see that there are a few hundreds of some kind of nodes and some other nodes, but it's not like this that you can just directly connect to computational nodes. We have to go through some manager, which is usually Slurm or PBS. In our case, it's PBS. and you have to ask for resources through the system manager, and then start the computation. So how to deal with this in terms of Hyperq, and I will demonstrate it too. So now I have here some consoles connected to the login node of the Carolina, which is the only place you can directly connect. And if I want to compute something, my program, what I could do in case of PBS, it's qsub command, and I can now specify what resources I want and what program I want to run. And then I have to wait in some kind of queue, and when the resources are ready, then my program will be executed and so on. We could technically we could run Hyperq in this way. So I will ask for some resources, and inside the job, once I will get the computational nodes, I will start the Hyperq, I will start the old infrastructure and compute my program. But even if it's technically possible, you will lose some of the features of the Hyperq, and it's that load balancing across the different allocation and so on. So it's better if you run the server outside of the computational nodes, and in our case, we will run the Hyperq on the login node. It's allowed in our supercomputing center, and it's not always the case. In some other centers, you have to use some cloud partitions or something like this. But it can be any other machine where the compute nodes can connect to. So I will run it on the login node. Of course, first I have to install the Hyperq. Again, I can just download the binary from the GitHub, or in case of IT4I, you can just load the module Hyperq. So, as I said, first thing I have to do is to start the server. So let's start the server. So the server is running, and now what I could do again is I could ask for the computational resources and then start the HQ worker in the compute nodes. But we offer one extra feature, and it's what we call auto allocation, and the Hyperq can do it for you. So you don't have to do it manually and ask for more allocations if your computation is still not finished, or care about not to deplete resources. We can cover it for you. So what I will not, instead of now qsub and starting the workers manually, I will just register a new auto allocation queue. So everything about the auto allocation is hidden in subcommand HQ alloc. I want to add a new queue. We are now running on the machine with the PBS, so we want to add the PBS queue. Now I have to specify time limit for the queue, which is the mandatory. I think that I just specified 10 minutes. Enough. And some command that I would add to the qsub, which usually means that you have to specify some accounts from the core hours budget will be spent, or you have to specify the particular queue. I will just demonstrate it on the QX, which is for some express computations. And this is all for this case, but usually for the practical use, you will have to add some more arguments. So what happened now, the PBS tries to do some trial allocation, to check that your argument is correct, immediately stop it. So right now, even we have created a queue. We are now asking for any resources because there is no task in the Hyperq that would utilize them. So the Hyperq will not submit the things. There is a called command qstart, which comes from, this is the PBS command that will show me that what is my, so I have no allocations in the PBS. But now, if I will submit some jobs into the Hyperq, like this, say just our favorite one, job is submitted. Now, because there was no worker where to compute, but we know that there is a registered queue, so the Hyperq asks some outer resource allocator for resources, and now we are waiting in the queue. Yeah, still in the queue. So we still have no resources, no workers, but hopefully we will get one soon. Okay, so once we are waiting for the resources, we can also look on what are other arguments. Right now, by default, we ask for only one worker, but there are more options. One of them important is this, is the how many workers per allocation I want. So right now, if we ask for something, we ask for one worker, but we can ask for more worker at once. This is especially useful for multi-node allocations. And another important option is backlog. It means how many requests in the outer scheduler we have in the waiting state, in the queued state. So in this case, we will see only one. We will see one. Now our allocation is running and one is queued. So the backlog means that there will be, as the backlog default value is 1, there will be only one waiting. But we can force to have more waiting allocations, and it will shorten the time that we have to wait for new resources, and usually we can also get more resources at once. But of the disadvantage is to have a bigger backlog that you may, if you have nothing to compute, the allocation is still fired, and by default it happened like this, that if there is nothing to compute, the worker will eventually switch off. By default it's 5 minutes. So right now I have a worker, I have my job is finished, and I still have one worker. It's in the running state, but I have nothing to compute. But it will wait for the 5 minutes, and then if no task arrived, it will be switched off. If I have bigger backlog, there will be more of this 5 minutes timeouts. But yeah, if I will submit something, I can compute more sooner. So this is quick overview how to run and deploy the Hyperq on the HPC machine. So this was the Hyperq, and now we are assuming that Hyperq is running. We have somewhere the server is running, somewhere some workers are running, and we want to submit some tasks, but we will not do it through the command line interface, like submit something like the sleep one, but I have shown you. But we will use the EVEREST that will submit the jobs into the infrastructure. So how it looks like, there are two, as I said, there are two APIs. One is task distributed API, and one is the distribute, which is super simple thing that I will just show you right now. I will import the EVEREST. I will now call this function distribute at the end, which just takes the data, which is some list of something which defines the computation. For this simple case, it will be just the numbers. And this is and distribute will somehow aggregate these data points according to the number of nodes. I don't know it in advance because I don't know how many nodes I will have, but I have to assume that there is some particular partitioning on this data, and I will provide a function that basically tells me what I should do with each partition in each node. So in this particular example, I will just summing the numbers that someone gives me. This defines what should happen with the result of each partition. So I'm also summing it. So each node will sum all numbers, and all these intermediate sums are summed together. So I'm just summing the numbers. Now I'm defining how many nodes I need, minimum 3, maximum 6. So maximum is quite obvious. I have 6 elements. I cannot create more partitions than 6. So it doesn't make sense to have more than 6 nodes. Which can be also automatically derived, but I'm using the argument explicitly to show that there is such option. Also, I can specify the minimum number of nodes. So if there are just 1 or 2 workers, it will not fire the computation. It will wait for at least 3 workers. So this is definition. If I will start program like this, it will connect to the Hypercube, submit the job, wait for the results, and give me the results back. Before I can start the program in EVEREST, what I need to do is actually set up 2 environment variables. One is VN, which is basically the virtual environment of the Python that should be started on each node. So I just put the path to the virtual environment, and it will be deployed on the node, and it's expected that the EVEREST and all your program is actually installed in this virtual environment. We have to also specify the work there, which has to be accessible to all computational nodes. Basically, in this path, the system will create some temporary files for the internal usage and the log files for this, what is happening. So if you want to have some deeper debugging, you can find it in the work. And once these 2 variables are set it up, you can just fire the script, and if the Hypercube is running, it will ask for the job. If you are in the auto allocation mode, it will ask for the jobs in the cluster. For the allocations in the cluster, then start the jobs there. Send the computation. Start the EVEREST inside the jobs, and when the computation is finished, it will send the results back to our Python. So this is it. This is how we can use EVEREST and Hypercube, how to deploy it in the cluster and use it. So thank you for the attention.